Right. Good afternoon, everyone, and welcome to another exciting episode of our Dalton seminar series. Today, we welcome Dr. Richard Foster, who currently holds a Research Associate Professor position at the Nuclear Research Institute for Future Technology and Policy, located at Seoul National University in South Korea. And his group supports research across all aspects of the nuclear industry, from reactor operation through to final waste disposal and decommissioning, while helping underpin national policy plans. So Richard completed his undergraduate and PhD studies at the University of Manchester and in chemistry and chemical engineering, respectively, and later including a 3-month secondment to the Korea Atomic Energy Research Institution, known as KAERI. His secondment provided to be a catalyst to pursue a career outside of the UK when he immigrated to the Republic of Korea to take on a postdoctoral researcher role in the Decommissioning Technology Research Division at KAERI. And in this talk today, you will hear about the Korean nuclear landscape as the country balances growing energy demands requiring new nuclear and environmental obligation, as well as decommissioning of aging facilities. And this talk will be followed by the Q&A. So if you joined us online, please put your questions in the chat. And if you're joining us live here, please raise your hand. We'll give you time to get your question to Rich. And the floor is yours.
Okay, thank you very much, Tatiana, for inviting me here and arranging this. It's good to see some old faces and some new faces, so hopefully you'll enjoy this. Tatiana did brief me that there's a range of people coming, from experts to students and stuff, so I hope that this topic or this talk has kind of found the middle ground, but if there's anything confusing, we can obviously go through it later. So I'm going to talk about navigating the road less traveled, meaning not going to the US, not going to stay in the UK, not going to Europe, but actually going out to Asia to study and work out there. So hopefully by the end of it, you'll see you can get some R&D success out in Korea. So I've broken this talk up into kind of 4 key parts of my journey, or what I've kind of done in the past. I'll quickly introduce myself and kind of career as a whole. Then my time at KAERI, where I spent 5 years before moving on to the stuff I'm doing now at SNU. And then finally, some kind of tips or what can be done in terms of collaboration for any of you guys, or more broadly, the UK in total. So quickly, as Tatiana very politely introduced, I did study here at Manchester for my undergraduate in chemical engineering PhD, then did a bit of secondment out in South Korea for a while, before then moving out there more permanently as a postdoc for 5 years at KAERI. And now I find myself at Seoul National University. The work I'm currently mostly doing is looking at waste forms, nuclear waste forms, and actually characterizing them, as well as some deep eutectic solvent work for waste treatment, resource recovery, and recycling applications. Just to kind of give a little bit of context to my background in terms of the science side of things. So my undergraduate is primarily organic and physical chemistry, before moving on to actual waste treatment in organic materials using X-ray CT for particle characterization. I then took a secondment out into KAERI, as Tatiana mentioned, in 2013, where I looked at nanoparticle development for cesium strontium removal, before returning back to the UK and working on some molten salts work with inorganic physical chemistry, and then finally doing a postdoc, which sort of led to the way to getting out to Korea again more permanently, where we looked at ion exchange as a recovery process for a backup system that they were developing out there. So I've kind of touched all aspects of chemistry. I tend to see myself as a master of none of them, but I kind of delve into all sorts of aspects. But when I came to the end of the PhD and the end of my postdoc, it was a case of, well, what do I do next? So do I stay in the UK, which typically is go to Sellafield or NNL for the vast majority of people at the time? Do I go to Europe, or do I go to the US? Again, most people were doing that in my cohort or my friends and colleagues, which is fine, but I kind of wanted to do something a bit different. I had an option, having been in Korea for a couple of months prior. And then during one of the meetings, one of the actual heads said, would you like a postdoc? So I said, why not? I took the view that if it all goes wrong, I can come back after a year. that was 7 years ago and I'm still there. So either I got lost or it's going quite well. To give some context for those who don't know, I'll kind of briefly introduce you to Korea as a whole. So Korea does have a lot of nuclear power these days. 26% of the power generation is nuclear based in Korea. So it's got a strong aspect for that. But they were quite late to the show. So you've got, for example, PWRs 1997, for example, 1977, were being commissioned and built. The last one being commissioned in 2019. So they're quite late to the party, but a very rapid expansion in terms of that. There is a bit of discourse at the moment regarding actual closing down of some of these reactors. So the previous government actually decided to go for a total phase out of nuclear power in Korea. The current government has essentially reversed that. So there's now this system where we're trying to decommission some while actually still maintaining others and keeping them operational. So there's this kind of divergence where we're still pumping into a lot of resource about actually building new nuclear powers while focusing on decommissioning them. In terms of UK regulations, these are the main ones in terms of the actual related organizations. These are the main ones out there. KAERI is where I spent much of my time, and that's actually the Base Research Institute. It's very much like NNL in the UK. We then have the Korea Power Engineering Company who basically build them. You've got Korea Hydro Nuclear Power, KHNP, which basically operates them. You've then got the fuel company, KEPCO NF, which basically makes the fuel. You've then got the new institute, which started in 2 years ago, which is the Institute for Korea Spent Nuclear Fuel. So that's actually about dealing with the spent fuel, preparing for final disposal. You have KORAD that actually disposes it, or will be disposing the fuel. And then you have several other regulators and things on the side. Just for context, where I spent much of my time is Daejeon, which is right in the center of the map, which is not marked. And then we've got much of the reactors down the east side, and that's where the actual disposal site and things are like. One of the kind of crowning jewels in many ways in Korea is actually their disposal site they've got right now. So this is actually the Gyeongju disposal site, where they're going to have many of the actual disposal silos here for underground disposal. This is essentially for low-level and intermediate-level waste. Not all intermediate-level waste, but kind of the lower end of the intermediate-level waste. And then there's going to be a surface disposal for very low-level waste, similar kind of DRIG that we have in the UK. One thing that they've kind of done with this is actually try to engage people from the beginning, the public. So they actually have a visitor center down here at the bottom, which is purposely designed from the beginning to actually get people in to actually see and explore and understand all the disposal. So they kind of very early on in the process recognize that they have to have this kind of engagement with the general public. And then you have the actual waste receipt area at the top. I can't show you anything else other than this nice pre-prepared slide, but we can get you more information in the future. One thing I want to highlight with Korea, however, is the decommissioning aspect. So one of the issues that we have in Korea right now, for all the good points about building reactors, disposal, etc., decommissioning is a big issue. Decommissioning is a big issue because they've started to close down in 2017, the actual first reactor being KAERI 1, and they have a very rapid decommissioning program is their plan. However, they have very little experience as a whole. So if you look at like France, Germany, Japan, etc., they closed their first reactors before the first reactor in Korea was even built. Now, I know it's taken a long time to obviously decommission a lot of these old reactors in the US and Japan, etc. But from the point of closure, all that policy work, all the research, all that's gone into actually closing them down. Whereas Korea is very, very in its infancy, which is kind of a big problem and something that we can obviously look to try and change or work on. To compare it obviously to the UK, for a bit of context, there's a lot of similarities between the UK and Korea in terms of decommissioning challenges. So there's no GDF, for example, for high-level waste. They've got aging facilities or full storage facilities, so that's a big issue. Obviously, there's research R&D facilities that have been used and developed both in Korea and also the UK, which obviously have bespoke challenges and bespoke issues to deal with. And also you're going to have things like socioeconomic impacts with redundant workforces when you close down all your reactors. However, there are some major key differences, which I think the UK is very strong in that could actually help with Korea. So, for example, there is no, in terms of Korea, there's no decommissioning centric authority to actually coordinate all the decommissioning. This makes a big challenge to actually coordinate that. There are limited storage spaces for spent fuel. So in the UK, we have Sellafield. For as bad as that may be, you actually have an overflow and the ability to actually store stuff. In Korea, there's no such place. They have to store it on their reactor sites, and they are currently full at about 90+% capacity. So they don't have space. So that's a big issue. And as I say at the bottom, they have very, very aggressive decommissioning targets with very limited or infancy in terms of the actual manpower and ability to decommission things, which is a bit of a problem. But this opens up a lot of options for joint collaboration, joint options to work with everybody and actually transfer and things like that. So on the side of the UK, obviously we've got a very established decommissioning industry, 20+ years of actually dealing with these things in terms of a coherent strategy, strong fundamental R&D knowledge, the list goes on. It's very, very good. Whereas in terms of Korea, they have very, very strong track record of taking technology development and actually applying it. They're very good at that kind of thing. They're a very highly driven workforce, and they can have many avenues for R&D funding. So there's a lot of willpower and a lot of interest there. It's just lacking the expertise, whereas the UK has that expertise, and it's about how we can marry that together. That's not to say there's not some challenges, particularly on the Korea side. Difference in health and safety, for example. The way health and safety is dealt with in the UK versus Korea can mean that you can have very rapid progression in Korea, but that may be at expense of some form of health and safety along the way. Again, no decommissioning centric authority, which means that there's limited D&D strategy. There isn't a coherent plan of how we're going to go from shutting this reactor down to actually decommissioning at the end, which is a big problem. And as I say, going back to aggressive decommissioning targets can also make a big challenge. That hopefully gives a very, very quick overview of both myself getting up to Korea and actually going there, and also Korea itself, kind of how it stands, and essentially is now on the verge of actually going into decommissioning on full scale, which is kind of where I come into in terms of my expertise. I've looked at decommissioning, look at waste treatment and things like that. But as I said at the beginning, when I had first finished my PhD and finished my postdoc, where do I go next? And that's where KAERI came along. So they very kindly offered me a position there as a postdoc, which I gladly took up. So it's actually based in Daejeon, which is in the center of Korea. And Daejeon is actually a science hub, and they have, certainly when I got this reference, 10 of the basically central fundamental science institutes. KAERI is one of them for nuclear engineering. There are others for chemistry, materials design, etc. So it's a really big hub of actual research and fundamental research there. It's a government-funded organization, but it does have aspects of industry collaboration involved and actual industry backing, which makes things can be easier for actually integrating from taking your ideas, taking your R&D to actually implementing them. And it was one of the first institutes established in 1959, so it's been around for quite some time. So I moved out there in 2016, and essentially I was kind of collaborating or being involved in a project related to industry. There was a catalyst, a waste catalyst that contained uranium, which was used by a company a long time ago, and that was then sat there as a waste that needed to be dealt with. So what I'm going to cover now is essentially what I did at KAERI for my work, and hopefully you can see kind of how we challenged that problem, how we tackled that problem, and how I got involved. So as it says, we've got waste to waste form. So I'll quickly introduce some of the waste itself, how we identified it, how we dealt with it, and actually how we went about solving the problem. So as I mentioned, there was a chemical company in Korea using the SOIO process for actually taking raw organic materials and actually converting them into polymer chains, acrylic fibers for further fabrication. And this used a uranium catalyst that actually contained uranium, antimony on a silica support. It had been used in Japan, Korea, and Taiwan, and now they're sat at the end of use in 2004, about 8,000 drums in storage. This was just left in storage on the industry site, and it had to be dealt with, and it had to be disposed of. The problem was that the waste was looking a bit like this. So we had the dry catalyst that was unused. We had wet catalyst and used catalyst, which contained a lot of organic materials. So unfortunately, due to disposal regulations, we can't dispose of it directly, so it had to be treated. There was certain constraints for actually the disposal site at Gwangju, where you can't have free water or chemical residues. The free water allowance must be less than 0.5 weight%, so we have to ensure that the material is dry. And actually, the particle size also has to be under a certain loading. You can't have, as it says here, you can't have 10 microns more than 1 weight%, and you have 200 microns more than 15 weight%. So essentially, these materials here that were just in these 8,000 drums had to be dealt with, no matter whether we get a volume reduction, whether we do any treatment to it, or whether we simply solidify it. But they can't be disposed as is. So something had to be done, irrespective of what we wanted to deal with. The overall goal, or the overall idea, was to take the SiO2 support, dissolve this up, and separate that out, and then take all the solid materials and actually solidify them and deal with them separately. So you'd end up effectively with 3 waste streams. You'd have the uranium waste that could be solidified and disposed of. You'd have this catalyst support that could be sent for free release or reuse, and any process effluents that could be cleaned up and dealt with. The overall goal was that we would work at KAERI for development of the process on the bench scale and up to lab scale. And then we'd have, working with another company, actually do pilot scale testing. The project timeline essentially was 2015, so it started just before I arrived for the lab and bench scale, and then we actually completed it in 2019 and 2018 with the pilot scale testing. Overall, the actual process we developed was split into 4 stages. So we had a heat treatment and support dissolution stage before a silicon precipitation purification stage, effluent treatment, and waste form manufacture. So essentially we could self-contain all of the waste in there, and we actually had ways to actually deal with the effluent, the uranium containing effluent, and pipe it through to the final glass ceramic disposal stage. In terms of demonstration, we had to demonstrate that we could actually use this process on the large scale. The issue we had was the fact, due to regulations, they were not allowed to move the waste to any site other than KAERI. But at KAERI, we didn't have sufficient space to actually run the pilot scale. So what this meant was that we did all of the testing with the real waste at KAERI for the lab scale and bench scale. We couldn't do the pilot scale. Then we simultaneously ran non-uranium containing waste catalyst through the lab scale, bench scale, and pilot scale testing. At the pilot scale testing, we then actually introduced uranium into that process, but not the actual waste itself. So it allowed us to follow the path of the uranium throughout the process without actually causing any issues. So as I say here, we took the uranium-free catalyst, combined it with UNH, and we're allowed to process it. So I'll very quickly give an overview of some of the actual work we did. So we looked at the heat treatment at the various stages, scaled up the process, looking at small scale filtration up to large scale filtration. And this essentially just shows you some of the actual work we did at that work. So this bench scale we actually set up within a couple of months to actually get it all set up and running and operating. And then the pilot scale we actually set up in its own self-contained, purpose-built building off-site that was allowed us to actually run this system at the full scale and test it at every unit scale. This was what the area I was particularly involved in. I was taking the photo, so I wasn't in it, but we essentially had the effluent coming from the silica filtration stage. We then had effluent transfer into this 1,000-liter tank, where we then did uranium precipitation with phosphate to actually draw out a lot of the uranium from the effluent, before then finally doing filter press and separation at the end. So very quickly, a lot of these I've got here just for people's information. I'll get onto some more of the detail later. But essentially, we had a heat treatment process in the beginning. This was an off-gas burner to burn off any of the organic material that was actually within the catalyst. We found that it was quite effective to remove a lot of materials, but we did find there was a lot of major chemicals 65 or 107 different chemicals, depending on the actual waste itself, which is not very good. This could then be dissolved using water glass solution with sodium hydroxide to actually dissolve up the silica support. This allowed us to suspend all the material, and any of the unfiltered material, any of the solids, we could filter out. As you can see here, we're able to filter it out, and then send that for disposal as a glass ceramic at the end, in the final stage. We found that as we scaled up to the different scales, so we actually got good volume reduction. One of the key goals of this project was to ensure that we got a good volume reduction across the whole process. We obviously don't want to increase volume, but we did also need to solidify and make sure that the waste was well contained. Here we're able to then implement a separation process. So we actually precipitated out the silica by changing the solution from being basic to acidic and reform the SiO2, but we retained the uranium in solution through forming this highly soluble peroxyl carbonate solution by adding peroxide and carbonate. So you can see here we had that the actual solution contained uranium, but the actual silica precipitated both at the bench scale and pilot scale without containing uranium. So we could actually separate that out. We found we got quite good separation, and we got less than 1 becquerel per gram of the silica cake, which is good enough for clearance at the end. In terms of the effluent treatment, this is essentially where I spent much of my time during my time at KAERI, focusing on this. We settled on a uranium phosphate precipitation process, so we're able to actually separate quite well. You can see here in some of the data, we can actually get below the release limit quite effectively with relatively small doses of phosphate relative to the actual uranium concentration, which is quite good. This did, however, raise a bit of an issue with obviously some of the other elements precipitating out as well, but we essentially got very, very good decontamination factors and very good percentage removal of the uranium, while the others were fairly low. So we could target uranium reasonably well. And then we could confirm it with bench scale as well. And finally, at the pilot scale as well, we essentially were hitting the release limit or below the release limit in terms of the final uranium concentration across all scales, which is very good. One of the issues, however, is adding phosphate. You then have phosphate released into the final effluent, which is a problem, so we had to take that out as well. We could do that through the addition of iron. And finally, antimony was contained in the catalyst as well. This also needed to be removed. The problem with adding the phosphate is it actually prevented removal of the antimony due to ionosphere competition. So we had to do a 2-stage separation process where we remove the phosphate out and then remove the antimony out as well, both of which could be treated as standard waste. So that allowed us to deal with that separately. As a little bit of an aside to this, I mentioned that while I was at Manchester, I did a bit of a postdoc collaborating with KAERI. We actually had a collaboration process where we actually tried to look at taking the effluent process that we had made and condensing it down into a single ion exchange system. And this was collaborated actually with Dr. Sherrard here at Manchester. It proved quite successful in lab testing. However, when we actually then moved to the real waste, we did have a problem where you actually got breakthrough coming after the iron. So you actually found iron was pushing off the uranium, which is a little bit of a problem. So essentially, we were able to use this process as a polisher rather than a main separation process, but it was a good collaboration nonetheless. Finally, taking all of the solid materials, we actually then needed to solidify them so we can actually dispose of them. Here we settled on using a glass ceramic system, partly because we already had some SiO2 left over from the effluent process that was separated, which was quite good. It allowed us to use that as a raw material in this process. And we found that we could actually also use the antimony that was in the system as well as an additional glass forming material. So we didn't have to add too much extra final material to these uranium containing wastes. We were able to more than match the waste form acceptance criteria. For example, compression testing for disposal of gongju requires 3.44 megapascals, but we're able to hit 195 megapascals, so we had no issue there, along with the leaching and the final radioactivity of 3,000 becquerel per gram. In terms of final waste, here we've got the dried waste, blended waste, the green body, and the final sintered body. These were for going into 200-liter drums. The final disposal, we settled on a disc type system, so we could end up stacking these to ensure that we had at least 85% of the drum filled, so we didn't have to worry about that to also meet that requirement. So the final stage of this was actually then looking at pilot plant verification, as I've kind of touched on. So we looked at all the unit operations from the heat, the actual dissolution stage through the separation, the adding the peroxide carbonate to obviously retain the uranium and the effluent before then precipitating that out. And we're actually able to very successfully separate out the oxide material, which would go to the final disposal along with the purified silica at all scales and at the pilot scale as well. This then allowed us to actually start looking at commercialization for this. This has not gone on any further because it's now been transferred over to the company that actually owns the waste so they can implement this, but essentially we've now dealt with that. So we were actually able to quite effectively make a reasonable process to take the waste, as I said, that was not suitable for direct disposal, and actually form a volume reduction process while also solidifying uranium and retaining it for final disposal. So there's just some outputs there. Oops, my apologies. Some just outputs there. For anybody who's got any interest, they can obviously see what we published regarding that. Finally, with KAERI, this actually led to me winning outstanding paper award for my presentation on the actual effluent treatment at our national conference, and then followed in 2021 by receiving the Early Career Researcher Award from the Korean Radioactive Waste Society as part of this work, which was quite nice to cap off quite a success at KAERI. So that was KAERI. That was what I did there, kind of 5 years condensed down into about 15 minutes, which is not so easy, but I hope that kind of gives you a snapshot of how we're able to, or Korea was able to actually very rapidly deal with the waste, identify the problems, come up with a process, solidify it, and all package it up, ready to take to a commercial company that can then deal with this. But after 5 years, my contract was up, and therefore it left me kind of wondering what to do next. Do I look to move somewhere else? Do I look to go leave the country? Do I stay? What do I do? And this is where I then moved to SNU, Seoul National University. Seoul National University, centered in Seoul, as the name might suggest, is essentially one of the first higher education universities in the modern age. And it's one of the prestige universities that has got a lot of a wealth of knowledge and center of expertise in Seoul, which is a good place to be, I guess. The actual campus itself is quite large. It was established in 1975 when it relocated, and it's currently ranked 11th in Asia, which is quite nice to be a part of. I'm actually located in the nuclear engineering and engineering area of the campus now, which is quite nice. And this is actually a view from one of the mountains looking over Seoul SNU. So my office is somewhere up in the top. So it's even a nice place to actually be, considering the center of Seoul can be a bit over the top. So where do I actually work? What's my lab now? So I actually now work in the Seoul National University Nuclear Fuel Cycle and Non-Proliferation Laboratory, which is quite a mouthful, SNU-NFC for short. And essentially, we look at the nuclear fuel engineering as a whole, with particular focus on molten salt applications, decontamination, decommissioning applications, and radioactive waste disposal. So we touch on essentially reactor and pyro processing, kind of the middle of the fuel cycle, all the way through to the end. So other than mining, we kind of touch on everything. And we have this split up into 3 teams. So we have a molten salt team, which is focused on that. We have decontamination, decommissioning, and waste management team. And we have a water chemistry team as well, focusing on that. As we say, the overall goal of SNU-NFC is to understand, monitor, and model chemical reactions and material performance for realizing advanced nuclear fuel cycle systems towards sustainable nuclear energy. In terms of what we actually focus on in terms of topics, the molten salts, they look at higher processing options, material corrosion properties, smart sensing systems in there. in terms of the decontamination team, looking at novel solvent applications for separations and also for decommissioning, looking at waste form characterization and colloid transport from those waste forms, while the water chemistry team is actually looking at a broad range, but centered primarily on the actual disposal facility itself and groundwater movement and modeling. As I say, we're based in the engineering. We have essentially 2 labs and 1 office. We have a wet chemistry lab, which has several glove boxes and furnace facilities, while we have a dedicated molten salt laboratory, which has a lot more facilities for molten salts. And we're currently building out an analytical laboratory, including fiber optic UV, 3D printers right now, but hopefully over time, we're going to be expanding that to rheometry, FTIR, Raman, etc., all to support the work we're doing. As a group, we've got a lot of national and international collaborators, which is something we're quite proud of and quite pleased of. Obviously, with the University of Manchester quite central in that, which is quite good. And also some of our other collaborators from Sheffield, in terms of University of Sheffield, and the Sustainable Smash team over there for waste forms, and Alethea here in Manchester as well. In terms of lab members, so I sit, even though I'm a research assistant professor, I sit under a professor, Professor Sung Che, as myself, and then we have several PhD students, master's students, and interns. In total, we have 32 people in our group, split across 3 teams, so quite a few people. So just a quick snapshot before I go into a little bit more detail of some of the work I'm doing right now, but a quick snapshot of some of the work I've been involved in. One is looking at deep eutectic solvents for decontamination and other advanced reprocessing options. So one of our students previously looked at using deep eutectic solvents for actually decontaminating steel surfaces, which is quite effective. And we've also looked at uranium dissolution within DS as well, which has been quite novel and quite new, which is quite nice. Another project we've been looking on recently is actually waste form characterization in terms of actual groundwater movement and actual corrodal colloid formation from the corrosion of that, which has been quite good for us. It's a new project that started a few months ago. So if there's anybody who's interested in collaborating, then feel free to reach out. But we're looking at actually how we can model this and how over time with these cement waste forms, geopolymer waste forms, there's actual colloidal formation and how that's transported. And then finally, the one I'm going to talk to you a little bit more in detail about what I'm actually doing right now is actually a non-destructive characterization of novel waste forms, which is actually a joint UK ROK project, working with Alethea Solutions here in Manchester. We're actually looking at the application of X-ray tomography to inspect the waste forms so we can actually build a safety case for their final disposal and final storage. So the project itself is actually collaborated with KAERI and SNU on the career side, and then actually collaborates with the some partners at the University of Manchester and also University of Sheffield. This was funded from the career side, and it was designed to actually engage and set up new research between Korea and the UK. And what we're looking at is actually development of geopolymer waste forms for final disposal of C14 wastes. So you can't obviously dispose carbon-14 as carbonates into anything that's high temperature formation, such as ceramics, glass ceramics and things, because you can obviously liberate the carbon-14. Likewise, using cements, they are not so great for long-term storage, and C14 being one of them that you've got a mid-term disposal criteria for. So we're looking at geopolymers as another option. The actual aspect of what I'm looking at is actually looking at these geopolymer waste forms and asking the question, can we develop and apply X-ray computed tomography for the ex situ and in situ inspection and validation of these waste forms to form their safety case and actually form a safety case for these. One of the issues with the way that disposal is done in Korea is we have a set number of acceptance criteria, such as compaction testing, leaching testing, which are all essentially a yes/no answer. For example, compression testing, you do the compression testing, you have to meet 3.44 megapascals. If you exceed that, then you can dispose. But the question is, what have you done to the waste during that procedure of compression? Likewise, leaching and things like that. So by looking at using X-ray tomography, where we can actually non-destructively look inside the waste, can we actually identify whether we've got cracks, porosity, problems within the waste form that we may affect final disposal or long-term disposal, and also actually look at applying this technique for the formulation of these waste forms. There's no way of knowing. The outside of the waste form might look great, you've formed it very well, but actually internally you've got things like flash setting, where you've got, actually, as this one's shown, you've got materials embedded which are not the waste, it's actually the matrix of the waste form, which causes issue for long-term disposal and things like that. So essentially, as I give an example here, the outside of your waste could look very good, but when you look inside, it's quite a problem. So as I mentioned with the compression, we have those issues there. So that's why we're going to look at X-ray computed tomography. Very briefly, how does it work? So some of these slides, or I've modified these from my colleague, Dr. Tristan Lowe at Alethea. Essentially, you have an X-ray source, you have your specimen, you have a detector. Like you go to the doctors and you get your leg X-rayed, you form a 2D radiograph. If we now rotate our specimen and take multiple radiographs, we can build up a 3D image of what we're actually looking at. So in this case, we could actually build up our waste form specimen, or here, some work that was done previously was actually looking at chrysalis, where we could actually look inside the object itself. We can then take our radiographs here and then do what we call segmentation, where we actually identify and allocate each of the voxels, each of the 3D pixels to different materials based on their radiograph properties or density or other measures. And then we can actually analyze our materials. So for example, here, you could say that you've got gravel, voids, and filler solids, for example, on a concrete sample or a geopolymer sample, and actually start to identify things like porosity, things like cracks, things like voids and things like that, which for long-term storage is quite important. You obviously don't want water ingress, egress that may dissolve your material, and this may be one way we can actually look at that. The wastes we're actually looking at are geopolymers with C4, planned to be C14 eventually, although everything we've done so far doesn't contain any active material, and either looking at carbonates or developed glass containing material that's been developed. So when we get the radiographs, so this is taken for some of our samples, first thing we want to do is actually process the data so that we can actually remove, hopefully, any artifacts that may have occurred within the processing. But we don't want to over-process this because we may then actually lose information within the material. So this is actually one of mine where I remove some ring artifacts within the actual data, which is causing a problem for the actual imaging process. But we can then see very clearly that we've actually got cracks and porosity within the waste form itself, which is obviously not a good thing for us to have. When we change the formulation from a sodium-based formulation to potassium-based formulation, we actually got a much more stable material formed, much more homogeneous, which we could identify through the use of X-ray CT rather than relying simply on other measures such as compression testing or other applications. Both of these actually passed the compression test at 3.44 megapascals, which when you clearly look inside and you actually see you've got all these cracks, voids and things, you're dictating that this can't really be used for final disposal. In terms of the CT, you then can look at segmentation and actually identifying. So here we can identify the crack in full 3D. We can actually start to take measures of these and get information. So here is a quick video where we can actually see going through the material itself. This is one of the waste forms that we've looked at in Korea. You can actually identify all these voids and cracks in 3 dimensions and see how much it expands throughout the waste. So if you had water ingress here from storing your waste over your geological lifetimes, you could actually end up with dissolving internally and actually have an issue with your waste form and final waste disposal. So here's just one of the data sets that I worked up very briefly, where we can actually identify the cracks, porosity, and things like that. One of the problems, however, is what is a feature? So when we're looking at CT and you're looking at voxels and pixels, you could argue, well, if I've got a single pixel, is that a feature? But the problem here is that that could be noise, that could be interpreted in different ways. So often people say, okay, you need to have 3 times your number of pixels to count as an object. The reason for this is if you've got a single feature in the middle, you need at least a minimum of 3 pixels being pixel on, pixel off, pixel on to say that there's an item there. But that's only a theoretical limit, or a theoretical threshold, essentially. What you need to do is actually have more confidence in that, and actually, are you confident to say what you're actually seeing? So you could then say, well, we have a threshold of 125 or a threshold of 1,000 pixels, let's say. So if we look at a set of data, so this is one of the data sets that I've quickly analyzed. If I look at the voids unfiltered, we've got a measure of porosity of 7.1%. But the problem with this is counting all individual pixels. If I say, okay, I'm going to have a threshold of 27 pixels, then again, we've got a lower porosity because now we're eliminating some of those smaller individual pixels. Again, if we go to 125 or 1,000, you can see how we can filter off our data. But the problem here is it's quite arbitrary based on just individual pixels and an arbitrary number. What we want to try and do is actually develop a more robust way that can be used regularly for calibration and also for object detection. This is where we've been collaborating with our collaborators in Alethea, with Dr. Tristan Lowe and his colleagues, to actually look at developing what are called spatial resolution targets, which allow for increased measurement confidence in what we're actually measuring. In principle, the idea to this is we make some form of disk or object, which we can put known defects into of known sizes. We then know, for example, if we put an object or defect of 10 microns into our target and then measure this in CT, if we can see that, we can know that our detection limit can be 10 microns. Likewise, if we don't see it, we can confidently say and have a greater confidence in our measure that that object cannot be seen. We can then rerun our final samples, our actual waveforms, and then calibrate and say, yes, this has a porosity of X to a confidence value of 80%, for example. Or we could have value Y to a greater or lesser confidence level based on using these targets. It also would allow us to then run on different systems where you can actually calibrate across, or use the same system on a different day or a different person. So it's about actually standardizing the system so we can get confidence throughout the process. So where we're up to on this, unfortunately, having some problems. So essentially developing these targets, first of all, we wanted to start with using the geopolymer itself. The reason for that is to ensure that you've got the same X-ray attenuation of your target in your final material. We then moved on to glass and alumina, all three of which had features larger than the minimal features we wanted to produce with the target. For example, if we want to add a 10 micron feature, but we actually have features already existing in the target of 100 micron, there's no way for us to identify which one is which for final target formation. Luckily, through some collaborators through Alethea, we've actually managed to work with some 3D printing companies that can now actually 3D print the targets we require with the set features we need without other defects being in those targets. And that is where we're essentially up to, and that'll be part 2, hopefully in a couple of months, when we actually get some final results on that for final disposal. So that's kind of some of the work I'm doing now at SNU. What I wanted to kind of finally wrap up on and kind of get to the end of this talk on is actually collaborative UK ROK programs, and also some of the lessons that I've learned having gone to Korea, worked with Koreans, worked with the UK, and kind of come back. And hopefully some of you guys who are looking at, starting your careers in PhDs or getting to the end of your PhD and thinking, what do I do next? You can actually perhaps pick up some lessons or tips from what I've kind of done over the time. So this hopefully summarizes very briefly the past timeline of collaborations between the UK and ROK, which essentially started around about 2013 with the signing of an MOU between KAERI and the University of Manchester, which led to my first secondment, in 3 months out there. We then had several projects set up between the University of Manchester and KAERI, and this was also backed by 2 large funding calls from the UK and Korea jointly, which have been ongoing. Essentially, a lot of these collaborations have kind of fallen into 4 aspects. being technical exchanges where we've kind of collaborated just in conferences and things like that. Actual spent uranium catalyst project was actually funded by KAERI to Manchester. The current project I'm doing with KAERI and Alethea and University of Sheffield. And then finally, some collaborative R&D programs as a whole. So back in 2013, a very, very young Dr. Sherrard actually signed a MOU with KAERI. And this enabled us to kind of have back and forth annual conferences and collaborations and talks between the two institutions, which is very good. A lot of this impact was not exactly primary impact, but very much secondary impact. So this led to things like secondments being set up. It led to things like collaborations, projects being funded and things like that, rather than necessarily a direct impact from this. This has continued all the way up until 2022, where again, a much older looking Dr. Sherrard came out and actually joined us for the EA Forum, which is the East Asia Forum on Radioactive Waste Management, and also joined our molten salt workshop held at SNU last year. Some of the lessons that I picked up from this is there's a lot of enthusiasm from both sides to actually have these collaborations, and they're looking to make closer ties, but there needs to be a much more constructive discussions on how you can turn these meetings to actual outputs, actual secondary outputs. So it's definitely something to go forward. As I briefly mentioned, I won't go into the technical side of this because obviously I've already covered it, but KAERI looked towards Manchester to actually develop an ion exchange system that could replace the effluent treatment process using phosphate for a number of reasons. This was an 18-month project funded at 400 million Korean won, which sounds impressive, but don't forget the conversion rate. And this actually led to 2 international conferences and actually 1 SAI publication as well, in terms of outputs, which is really good, but there was a number of lessons learned, one of which being poorly defined targets. One of the things I'll touch on a little bit at the end, if we've got time, is that there are different ways in working from the UK and Korea, and things when you say something, you know what you mean in those words, but that has to be translated and maybe interpreted differently. So one of the issues we had was poorly defined targets on both sides, did lead to some issues. No access to the actual waste for obvious reasons. We couldn't ship 8,000 drums of waste to the UK for various obvious reasons, but that also caused an issue. And then things like financial reporting standards. There are different, admin operations, admin standards. There's different timeframes between UK and Korea. It can cause some big issues. This one, third case, is actually where it's being funded from Korea to here. So this is all coming from Korea, which is what we're working on now. Some of the benefits of this have been quite a lot of freedom from the Korean side to actually establish these new links. But again, it can then be difficult to actually engage with the UK side that don't have that financial funding or that financial commitment. So it can become quite an issue with those kind of things. Finally, these are the fourth case or fourth type of collaborative R&D. These are the big funded projects that have been done previously between UK and ROK. As I say here, there's been a decent funding rate, 33% success and 50% success, with about 2.2 and 1.6 million in both rounds. And hopefully, COVID now finished, there may well be a third round coming up in the future. When this will happen, I'm not sure. There are some links here you can kind of go and check out for details, but we may well see things coming down the line. More for kind of you guys, for what you may want to look at for if you want to look into funding or opportunities with Korea. There's several options. There's the NRF, they are the national funding body. They release all the funding calls for all aspects. You can always check the website out. Obviously it's Korean, but you can get a translated version. This is more for those researchers already in Korea, but that you may well find something you want to look at applying for and kind of reach out with someone. You've got the Korean Nuclear International Cooperation Fund, KONICOF. This is actually supports primarily Koreans, but also supports other way of actually having researchers, particularly students, PhDs, postdocs, coming to other countries to actually learn. And finally, there is the Brain Pool Korea BP and BP Plus program, which is designed solely to bring researchers who are outside Korea into Korea. They are essentially for those who have completed their PhD. It's essentially a fellowship that's for up to 3 years, reasonably well funded, reasonably well backed, anywhere from 5 million to 25 million salary, which again, don't forget you have to convert that. But there's a lot of support there to actually get researchers who are coming to the end of their PhD or have done a few years postdoc into career. So it's definitely something you might want to check out down the line. However, I'll just finish off with a couple of slides to kind of give you some differences between UK and ROK styles. In terms of funding calls, so if you're looking at funding calls in Korea, they typically open March to May every year, but they're very, very tight turnarounds. You can go from the call being announced some like May, for example, and it'd be fully funded and signed off by June. So you've got to act really quickly if you're interested in these kind of things. They don't dilly-dally in Korea, kind of get things through. Funding duration is something that I should point out because it's something that often confuses people. The years for funding are based off the calendar year. So it ends on the 31st of December. As I said here, if you start a project in April, the first year will be classed as the 31st of December, therefore being 9 months equaling 1 year. Likewise, if you start in November, your first year ends 31st of December, therefore 2 months equals 1 year. So if you have a 3-year project starting in November, then you actually have 2 years and 2 months, which is different to the UK, which again, going back to some of those previous projects, has been kind of an issue or a mismatch in admin and things like that. Also, they have a 3+2 rule equaling 5, where PIs can have only 3 roles as PI, but they can have a further 2 projects as co-I with national funding. So that's something to actually remember and think about. And finally, in terms of how research is often done in the UK, you kind of start broad and you narrow yourself down. You kind of look at different things and say, okay, this is interesting, or we need to go and look at this to support this other aspect of work. So you kind of get this very funneling approach in terms of UK research. In contrast, Korea goes, we have a problem, there's a solution, let's go, which is effective in terms of progressing further, or perhaps getting to the end of the goal and solving your problem, but you end up with this very, very narrow type of focus, which has its issues. One example would be this catalyst waste we worked on. At the time when we started, there was no regulation for antennae release, so it was never considered. I, however, having worked in the UK, when that doesn't sound right, kind of came up with a way of dealing with it so that when it did ultimately come up to be a problem, we're already prepared with an answer rather than having to go back and re-research and resolve the problem. On the flip side, this kind of works well to represent actual PIs. Traditionally, in the UK, often the PI is quite focused on their research within quite a narrow field and become very much an expert in that field. Whereas in Korea, they're much broader. If you looked at our professor and obviously what we're doing, we focus on the everything other than mining on the fuel cycle. So you've got actual reactor design, reactor operation, waste forms, waste treatment, you name it, we do it. We have this very, very broad approach rather than being very narrow. Just a couple of tips and tricks. If you're going to work with any international, so as an individual, obviously you can start searching for funding, being prepared. One thing I really want to point out is adapt to cultural differences. There are cultural differences, whether you go to Korea or whether you go Europe, wherever you go or choose to go. And that's something you need to be able to adapt and learn to communicate effectively in terms of your work. And while being collective, so as a collective thing, if you're actually working with people, the really big important thing to actually be clear on your expectations and outputs from both sides. Again, this goes whether you're working with Korea, working in China, working wherever, there are differences in culture and differences in aspects, and you need to be able to understand what those differences are and defining them very early on. Okay, let's look at the draw. Finally, as individuals, a couple of tips for you guys who do your PhD. It's too late for you, Clint, I'm sorry. You know, define your core research. So what are you interested in? What do you want to do? Note down the ideas that you come up with and work on them over time, even if it's not your main project. You can always pull them out of the bag later. Be open-minded and flexible. So if someone gives you criticism, take it on board, assess it for its own merit, and then decide to ignore it or follow it. And then take the path less worn. I've been lucky, I've been quite successful by doing that. It's not for everybody, but for those of you who are interested, I strongly recommend it. And then be extroverted as well. Make sure you network with people. Be genuine in terms of your research and how you approach people. Provide something before expecting anything. So what can you offer to the table? What can you offer to the problem before just expecting things to be given to you, things like that? And try to identify what's not seen by others. So come at a new problem and look at it from a different angle and try and offer something new that can solve the problem. And find your passion. I know that's a bit of a cliche, but you always, if you're interested in something you're doing, you're going to find it a lot easier when it gets harder and tougher. Finally, I just want to make some special mentions. I think it's often overlooked not to mention people like this, but I think also as well, as an example, you should try and find people who can support you along the way. So find someone that you look up to and actually respect. That for me, this was Nick Bryan. For those of you who may not know him, but anybody who does, he was very good and very influential. Find someone who trusts you, whether it's right or wrong, but allows you to be flexible. I found this in Clint. He was pretty happy for me to go off and try things, learn things, fail, come back, solve the problem. Make sure you find someone who's willing to criticize you and pull you up on things. I found that in Francis Livens. Again, accept criticism when it's valid, take it on board, learn from it. But equally, find someone who's willing to fight your corner, defend your back, and actually guide you in the right direction. I found this in Mark Ogden with some of my work I did. Find people that you want to work with and you actually look up and think, I would like to be where they are or what they're doing. I've been lucky to find that in Dr. Tristan Lowe at Alethea. And then finally, find good peers that you want to work with all the time. Again, I found this with James Amphlett. Obviously, this is just a few examples, but I hope that you can kind of take away from that to find different people that you can kind of look at and use and develop over time. And finally, the names keep getting longer, and therefore I'd like to thank everybody. And then finally, thank people who we have in our group for the work we're doing right now. And I hope that that takes bang on time. And I hope, thank you very much for listening.
Thank you very much, Rick, for this insightful presentation. We now have time for a couple of questions. Do we have any questions from the audience here?
Two quick ones. One, you mentioned a little bit about reprocessing. Are the Koreans like really interested in decomposing the fuel cycle, or is that more of a kind of we're just keeping some options open for the future? Maybe if we go big into nuclear.
Considering the conversation, considering the nature of this talk, pyroprocessing is what they're looking to. That is what they can do. That is what they've become experts in. And that's something they're trying to scale up. Obviously, there's a lot of interest now with molten salts in a broader sense. But yes, they are looking at options that can be dealt with pyro. Obviously, there are issues with non-proliferation in Korea. So you can put two and two together, why that might be an option for them. And that's as much as you get from me.
And the second part was you mentioned resource recovery.
Yep.
Is that from spent fuel or?
So the resource recovery that I'm doing is nothing to do with that. It's actually to do with LIBS batteries, so actual lithium-ion batteries. I didn't feel it was like suitable to really talk about in this project, this presentation, due to obviously the audience. But one of the side projects we actually have was kind of a fluke spin out from some of this deep detected solvent work we've done in the past, where we actually found some options potentially for doing that. But that resource recovery is very much, lithium, cobalt, those kind of things.
Thank you.
Any more questions?
Okay. So that 3D image which you showed with regards to the fidelity of how you pixelate it, what happens if you scan the same item twice or three times? Is there any kind of random assumption when it finds this pixel and says, this is this or this is this, or would you get exactly the same processing every time you scan it?
That's essentially one of the reasons why we're looking at going down these targets and actually looking at these spatial resolution targets. The easy answer is no, you're not going to get the same. That's likely because of instrument use, things like heating up the X-ray tubes and things like that. You're going to get different attenuation. Operator use, how they choose to set it up. whether you actually replacing the sample, you change the dimensions between the source, object, and detector, these kind of things. Developing these spatial resolution targets, knowing that the features are unique and also measured independently and characterized independently, will hopefully allow us to actually remove many of those variables so we can get much more repetition. If you think about how we could potentially apply this for actual disposal site, at the Gwangju disposal site right now, they have a conveyor belt for the drums with a single 2D radiograph imaging. That is simply just to say, is it full with something? That's it. Going forward, if we can actually implement this kind of thing on a more robust scale, we can actually use it to automate and therefore put through all these waste in a 3-dimensional scan a lot more rapidly to actually get far greater amount of information. To do that, we want to obviously be able to replicate the system very rapidly, and also removing the human element means we can actually automate a lot of these systems, hopefully with computational work and actually much more rapid. So the simple answer is no, you wouldn't get the same scan all the time. Hopefully going down this route, we can actually start to essentially get the scans to be the same or much, much closer into reproducibility over time. I hope that answers your question, Seven.
Yeah, really good. Obviously, if you can turn the samples over to the test samples and say, and it gets the same amount of porosity either way up, and that's going to be good.
Yeah. So as I say, some of the criteria for the disposal site are things like porosity, or it's actually the volume. So it's going to be at least 85% full. So obviously the porosity issue there, but it's more looking at the cracks and things, those kind of damages to the actual waste form itself. And it's all about building the safety case. So it's not about discovering something new or finding something new or groundbreaking. It's more about building the safety case. So if we can say that, we've analyzed this, and yes, there is some porosity, but with all other checks involved, it's still going to survive longer than the actual RI itself, in the case of C14 being 5,000-year half-life, then we can build that safety case to say that you can accept a certain level of porosity or a certain level of what I'll call damage, for want of a better word, in the actual final waste form, because you're never going to get pure waste forms. The other issue is a little bit of an aside. A lot of work that's going on right now with copper canisters, for example, is actually looking at modeling and corroding them, because obviously you can't do an experiment for several million years. The problem with that is it's based on 3D meshes that are perfect. So it's saying we've got a 3D cylinder of copper, how long does it take to corrode through to the actual waste? By doing something like this, where we can get very good measurement confidence of what we're analyzing, we could then build that into a model and actually start to model the corrosion based on known parameters of the waste form, combined with the 3D meshes we can get from CT, with a confidence level of X, Y, and Z. And therefore we could put all that together and say, right, we know that this waste form will last 10,000 years with an 80% confidence level, or if you want 100% confidence, it's actually 5,000 years based on the models and that kind of thing. So it's about bringing this interdisciplinary work together and putting it all together into that building of a safety case to say, you need a waste form for 10,000 years, this one can last 50,000 years at a 95% confidence level. There's your safety case.
Thank you. Do we have any final questions?
Sorry if I missed that, but in your current work with SOLV, are you capable of working with active samples in like molten salt or decommissioning labs? And if so, what kind of characterization can you do with that?
So in our lab right now, we can't use any active material. So for context, our team moved from KAEST in 2021. So 2022 was spent rebuilding the labs, actually at our facility. And then we are currently in the process of building, or will be looking to build, a new nuclear engineering building with an active lab in, which will be run and operated by ourselves. So we can't do. However, we have access to KAERI and other facilities where we could, in theory, run some experiments if we wish. As for their characterization capabilities in their active labs, I don't know. Our plan is to have XRD, rheometry, TGA, etc., actually in the system, with the TGA and rheometer hopefully being in glove box conditions, within the facility. And we may look at other options down the line. As always, we had a grand plan of a nice large RI lab, and then, you know, things change, policy gets involved, and then it gets smaller and smaller and smaller. It happens to the best of us. It happens here, it happens in Korea as well. But there is still a primary goal of having some large equipment and small equipment all active, several glove boxes and things like that. I could talk about that at another time, or send you information if you're interested once it's kind of built and developed further.
Sure, thank you.
The last one.
So you mentioned obviously the infancy in terms of decommissioning. And I'm curious, given the timeline, so has there been a steady transition generally from the active expertise over to decommissioning in Korea, or is that a barrier that just doesn't happen?
No. So context, my old team, my old department was a decommissioning and waste treatment team. They were all well into their 50s, the vast majority of them. When I left, I think the average age shot up by a good 5 to 10 years. I was kind of holding it down as a youngster, which is quite nice. So there's definitely an issue there. Not wanting to get into politics, often what happens in Korea is they can change on a dime sometimes. So previous governments wanted decommissioning, newer governments do not. There isn't always a coherent plan of how you would chop and change and digress that. To talk differently from the UK example, you've got the NDA. It doesn't really matter what happens with government or other policymakers, there's a broad consensus of direction of decommissioning. So you can kind of change course slightly, but you're actually still going the same way. And that's something I think is lacking in Korea. And I think is something that's going to be a big problem. Essentially, decommissioning really kind of came to the forefront of Korea a number of years ago with the change of government, although it's always been in the background. But that kind of knee-jerk changing can bring its problems, shall I say, or issues along the line. Yeah.
So do you think there's opportunities for, let's say, generally Western people to come into Korea, or I suppose what's the biggest hurdle you think? Is it the Korean end, or is it the sort of our end in the Soul world?
I think there's a lot of opportunity for Western expertise to go to Korea and actually guide them in how they deal with things. I think on the Korean side, there is a lot of understanding and appreciation that needs to happen. There's a lot of funding for that. There's a lot of institutes, Konikoff for one of them. I've been involved in a decommissioning summer school twice in Korea, where they actually get international experts to actually do and talk about decommissioning. So it's very much on the radar. The issue, I guess, is how you approach that subject to the Koreans without feeling you're dictating to them, and actually working with them, with their needs and their goals, and partaking your expertise to them, rather than simply saying, hi, this is how you do it. And then don't look at Sellafield, by the way, that kind of thing. You have to be, a little bit thing, but there is definitely on the top level, there's definitely an appreciation for Western knowledge. And you could leverage the Korean kind of drive in industry and practicality aspect with the knowledge of the West, I think.
We have one question from Zoom, so I think it will be a nice one to finish off.
Yeah.
So as a chemical engineer, what made you interested in studying spent nuclear fuel management? Also, when you first moved to South Korea, how did you overcome the language barrier?
Okay, the second one's easier to answer. I didn't. So my goal was to try and learn Korean and to really speak it. So I can get by on daily life, but it very quickly became evident to me, and to be fair, my other colleagues, that speaking Korean on such things such as uranium handling or other technical aspects, when the other person may not understand Korean fully, was a recipe for disaster. So we very quickly realized that actually just working in English was much easier. And then obviously there is things, hazards and things that get flagged, we can readdress that and kind of go through that individually. Also as well, Koreans want to learn English. So I had several people that I was kind of helping with that. So it kind of, my learning took a back burner. Regarding the other aspect, I wouldn't call myself a chemical engineer other than the piece of paper from the school that I graduated from. I'm definitely more the chemistry and then materials. As I say, I'm a bit of everything. In terms of getting into this field and things, I think it's just one of those things you kind of a little bit fall into it, and then you start to carve out your niche as you go along. And particularly with the KAERI project I did, the waste catalyst, it was really nice to kind of see a problem and then solve that problem at the end with a nice full process, rather than trying to develop something new or trying to find the blue sky research, which can be very exciting and interesting. More that aspect of there is a problem there that no one else is dealing with, and you've been asked to deal with it, and then you find how to deal with it at the end. That's quite rewarding in that sense. So, yeah.
Right. Thank you so much. Let's thank our speaker again. So with that, we'd like to finish our seminar, and thank you all for coming.